The topics of my talk are solar and atmospheric neutrinos. In my former talk, I talked about the properties of neutrinos and the underlying theory of the standard model of particle physics. But today, I like to emphasize solar and atmospheric neutrinos. I choose as an example the Super Kamiokande detector because it can detect the solar and the atmospheric neutrinos. It's a multi-purpose detector. You can see it over here. It is situated in Japan, 1 kilometer in above the mountain in a mine. You see it is a cylindrical tank filled with 50,000 tons of ultra pure water. And it started measuring on the 1st of April for detecting atmospheric neutrinos and also solar neutrinos. Here you have an insight in the tank. You see the photomultiplier tubes, which observe the light which is caused by the reactions, which is a Cherenkov light detector. And here you see an event display of a muon-like event which occurred there. And here you have these characteristic Cherenkov rings, which are detected by the photomultiplier tubes in the whole detector. What should be mentioned here is that this detector can do a reconstruction of the direction of the incoming neutrinos and also determine the type of flavor of the incoming neutrinos. So let's stick now to the topic of the atmospheric neutrinos. What are atmospheric neutrinos? If cosmic rays from the outer space of the Earth, which is predominantly protons, hit the atmosphere, the outer molecules of the atmosphere, which is predominantly oxygen and nitrogen, they produce in strong interactions pions and kaons. These pions and kaons decay. They decay very rapidly, leading to muons and muon neutrinos and electron neutrinos. I have made here a sketch of a pi plus decay. The pi minus is equal. So you expect two types of muon type neutrinos and one type of electron type neutrino event in the atmospheric neutrino flux. What they did is to make a ratio of ratios from the measured neutrino, muon neutrino-like events to the electron neutrino-like events. So if we understand the whole theory and we understand the flux right, this should be, the ratio should be 1, because here you see we have two muon-like neutrinos and one electron-like neutrino event. So this should be 2 divided by 2. Which should be 1, but what they measured was a ratio of 0.6. So about 60% of the flux was missing. No? Here you see a sketch from the events which were downwards. So they equally to the prediction, but the events which were detected from the other side of the Earth, only half were detected here, no? Which is seen over here. Okay, so we have a problem in the sector of atmospheric neutrinos. Let's switch to the solar neutrinos. To understand the solar neutrinos, we need a solar model. This was done by B.A.L, and he did predictions of the solar neutrino fluxes. It should be mentioned here that the Super Kamiokande detector has a threshold of about 6 to 7 MeV, so he can only detect the neutrinos which emerge from the boron 8 decays. The HAP neutrinos have low flux, though predominantly they measure boron-8 neutrinos from the sun. Here is a prediction of all the flux of the solar neutrinos, which are electron neutrinos, and here the distribution where they are created. You see on the x-axis the radius in relation to the radius of the soul, and the quantity of produced neutrinos. So what we see is that about 10% of the radius we observe boron-8 neutrinos over here with a super Kamiokande detector. And what I did, I used the image which is publicly available on the site of the Super Kamiokande page, where they have reconstructed the spatial of the emergency of the electron neutrinos in the sun. So this is the reconstructed electron neutrino signal of boron-8 neutrinos directly detected here on Earth. You see that it is somehow in the interior of the sun, so the neutrinos are ideally suited for measuring processes inside the sun. But we have another problem over here. The neutrinos on the way from the sun to the Earth, only 1/3 of these boron-8 neutrinos have been detected. In 2001 and 2002, the Sudbury Neutrino Observatory showed that the conversion of solar electron neutrinos into muon or tau neutrinos was the solution for this missing electron neutrinos in the Super Kamiokande detector, because with their detector they could measure all the neutrino flavors, so they had a direct measurement of the total flux of the neutrinos. And we end up with a problem of missing neutrinos of the solar neutrinos and of the atmospheric neutrinos. Pontecorvo did a theory where he used a modification of the standard model. The neutrino flavor eigenstates are over here, which are treated as a mixture of mass eigenstates. And here you see U is the mixing matrix of these neutrino eigenstates. So if we calculate this matrix, it's a rotation, a product of 3 rotation matrices. So
okay. 2 minutes.
What you see over here is a short form of cosine for the theta of the mass eigenstate I A j. And here is a sinus. No? So with this ansatz, we can calculate the probability whether an electron neutrino behaves as an electron neutrino at the source and at where they are detected. Here you see delta m I j, which is the difference of the squares of the mass eigenstates. And L is the distance from the source, and E is the neutrino energy in gigaelectron volts. So what we have to take into account, the neutrinos travel through the material, which is dense material with electrons inside, through the sun. And the same occurs here when they enter into the Earth. We have a day-night effect. At night, the detector is on the other side of the Earth, so the neutrinos have to travel through the whole Earth. And Pontecorvo and Mikheyev, Smirnov, and Wolfenstein did theory of matter oscillations due to the fact that the neutrinos, the electron neutrinos, could react with the electrons of the dense material of the sun and of the Earth. We have to treat them with somehow a Schrödinger-like equation, where emerges here the neutrino eigenenergies in vacuum. In this matrix, here we have the mixing matrix, and we have an effective potential where emerges here the electron density, because only electron neutrinos can react via charge current reactions with a dense matter, so they are infected of the matter effect. Muon neutrinos and tau neutrinos are not affected. So this leads for the results that we if you take this theory to fit the solar and atmospheric neutrino data, we get two solutions. We have here the mass difference of the atmospheric neutrinos and the solar neutrinos in the normal ordering hierarchy, where the mass eigenstate of the nu1 is lower than nu2 and lower than the mass of nu3. Or we have the inverted, which we cannot exclude, but which is also a solution to this problem. So only the atmospheric and the SOL measurements are switched. When we do the best fit of all the measurements of neutrino oscillation experiments, we get these values to fill in our matrix for doing the calculations. This is our data. You see here the reference of 2019. I like to mention here the theta 1,3 is yes, the sinus squared theta 1,3 is a very low value, and here's the mixing phase, which is imaginary in the matrix. So this is responsible for CP violation effects. Doing the conclusion, neutrino oscillations explain the difference in predicted and measured neutrino flux of solar and atmospheric neutrinos. At least two neutrinos are proved to be massive, but neutrino mass generation mechanism is unknown to date. Neutrino oscillations are experimentally and theoretically established extensions to the standard model of particle physics, but it has many free parameters which have to be determined by measurements. It gives us a clue to the problem of matter over antimatter symmetry with the CP phase, which emerges there. So neutrinos are very challenging. In April this year, Nature did a publication of their journal of science, and there are maybe new results of the Super-Kamiokande experiment, because it is written here, an indication of matter-antimatter symmetry violation in neutrinos. So thank you very much.
Thank you.
Ok.
Ok. Então, perguntas?